Welcome to Cryptography and Hardware, the 8th session. Up to now, we have seen many different types of the AES implementation, and this is the last session about the AES, I promise. Yeah, and we are talking today about the smallest possible implementation of the AES. Means that you kill the latency. It doesn't matter how long it takes, you just want to save some gates. Yeah? Means that you are under super high pressure and reducing the size, you have very small part of the area, and you want to do something in a way that it doesn't matter how long it takes. I want to just make something which is super small, as small as possible. Yeah. The first design of this kind was known as Byte-serial implementation. It means that you have just single instance of the AES box, which is mandatory. I mean, smaller than that, you cannot probably go. You will see that there is actually possible to go even smaller than that. Yeah, and then you have one instance of the AES box, and then again how you can reduce the area of the mixed column, because a mixed column is also a couple of XORs, you know, for multiplication by 2 and multiplication by 3, and then again a lot of other XORs over this result of multiplication by 2 and multiplication by 3 of some other bytes of the state, then to provide the output of the mixed column. Now, then how we can save. What is important and you should consider, it doesn't matter how much you try to reduce from the size of the logic, the registers actually you cannot reduce. 128-bit for the state of the cipher, 128-bit for the key, you cannot go less than that. And then the area of the register is not as small. I mean, registers are usually small. And then many designers during the last, I would say, 15 years tried a lot with many different tricks to reduce that area as well. For example, you know that registers require some enable signals. Yeah? Sometimes you want to store, sometimes you don't want to store. Yeah? Or sometimes you want to stop the computation, means that you have to disable the registers. Then many people or many researchers came with some ideas. Okay, instead of having the registers with enable signal, let's clock gate them. I mean, I can explain it shortly. Means that you have a register which is provided by the clock, and then you have enable signal. And then this is, of course, larger than one register without the enable signal. And then you have, for example, 128 of them, or even 256 of them. Then if in some clock cycles you want to stop the computation, then instead of instantiating 128-bit register of this type, then you can integrate or instantiate the normal registers without any enable. Yeah, but then you want to control. Then you bring actually the clock over the AND gate into the enable. But this is not working well. I mean, probably you learned this during the digital technique, I don't know. Yeah, when the clock is 1, and this area, and then enable signal actually changes, then you get a positive edge of the clock here. Yeah, that it should not get. Yeah, means that this is glitchy and this is not the correct way to do. Then the clock gating should work actually with a latch, means that you have a latch here and the enable is here, and this is controlled by the clock. Means that then the clock is 0, then it doesn't matter actually what happens with the enable. When the enable is 1, then this value, the result of this value, the result of the latch stores this, because it's transparent, but it doesn't affect on here. It only affects at this positive edge of the clock. Yeah, and this is the correct way, means that you can have this only once if the enable of all the latches are the same, or enable of the registers are the same. Then instantiate this guy 128 times, and then you have this, only once. Then you can reduce the area. I mean, this is not dedicated to AES or any other thing. If you have many registers like this, then it's sometimes actually is done like this. But it's, I mean, generally clock gating is not something which is common. It's not really recommended because it provides also clock skew. Yeah, I mean that some registers receive the clock earlier, some others a bit later, and then if this is large, then there is no guarantee that the circuit works correctly. Good, but they are the tricks that can be done in any implementation. This is not dedicated to AES. Yeah. Then what happens and how we can make this the AES Byte-serial? Means that it's a shift register, but it's working serially. The first design in that fashion or domain was built like this, that you have this box, and this is taken to this box. If you remember, it was 0, 1, 2, 3, and so on. 4, 5, 6, 7, 8, 9, 10, 11 bytes, and then this is loaded here during this box. Of course, there is here one key, and then the idea was to shift this exactly in the fashion that the byte numbers are. Means that first 0, and then 1, and then 2, and then 3, and then 4. I mean everything is shifted. In this direction. Then what do you do for the mixed column? The first implementation was like this, that you have anyway a mixed column 32-bit, and it's coming actually here. And then at that time, when you do a mixed column, you shift in this direction. But again, you need a shift rows, and again, another multiplexer to decide which one you perform. Good. Then how many clock cycles you need per cipher round? You need 16 for the add round key combined with the box. You need 4 clock cycles for the mixed column, and you need 1 for the shift rows. Of course, I mean, first shift rows, of course, shift rows before the mixed column, Then how many times is 21 clock cycles? And then one question or big question is, what do you do with the key schedule? Then you need 4 clock cycles to perform the key schedule, because you have one instance of this box. Then when do we do this? Then the best is actually to do this here, key schedule, during the mixed column, because this box is not used. But then I need to again remind you that this is the key module. And during the time that we provide the key, I mean this key, wait, this key, this one, then we actually need to provide it also in the same fashion. Means that we shift and rotate in this way, means that after this we bring it back to here. But then when you want to perform the key schedule, if you want to say, hey, I perform the key schedule similar to what we have seen for the column-based implementation, means that you perform first the SPOCs over some of them. I need to probably draw it for you to remind you how it was. We had 4 words, and then this was coming to the G function, and then XORed here, and then XORed here. Bring it back, and this is also result. And actually this guy, this guy actually is corresponding to this column. No? Then what you need to do, you need to perform the SPOCs over this column and XOR it with this column. You can, of course, do it in 4 clock cycles, but then you may think of, okay, I need to update these 3 as well. Yeah? But then if you have those many SPOCs, the implementation is pretty large. What is done is that during the key schedule in these 4 clock cycles, the bytes, or let's say the columns, can be rotated upwards. Means that this is rotated like this, and this guy is also rotated like this. Yeah? During this time, you take the output of this one, this guy. Why? If you remembered in the G function, something is rotated, yeah? Some bytes are rotated. You give it to the SPOCs, I mean the same SPOCs which was at the top, and then you bring it here, you XOR it with this guy, and then save it here. I mean shift it, yeah? Everything is shifted. Then after 4 clock cycles, what you did, you applied the G function over this. Means that you have actually this guy done. Yeah? This guy is done, but nothing else. But when you are using the key, again here, from here is taken. Yeah? Look here, it's serially taken from here. You can do the XORs that you have not done, this guy, and this guy on the fly. Yeah? Means that you take this, yeah, and then again give it to this XOR, you save it back here during the time that you use this. Means that you only need 8-bit XOR instead of those many XORs that you need here. Then during the 12 clock cycles, yeah, you provide already the XOR between, you mean this guy was over, yeah? This was over. This we have. We need to just XOR it with this and have this. We can do it in the 4 clock cycles. These 2 guys in the next 4 clock cycles, and these guys in the next 4 clock cycles before we really use them. One more time, yeah? During the mix column, now these 4 clock cycles, what we do, we update and provide the next subkey only for this column, only here. Using 4 SPOCs, using 4 clock cycles in one instance of the SPOCs. And since everything is rotated upwards, I mean it's not rotated over the entire 128-bit or 16 byte or let's say 16 byte state, it's rotated over the column. And then you have this ready. This is completely ready. But then afterwards, shift rows, of course, we don't update the key schedule. This is completely separate. But then in the next clock cycle, when we performed add round key and SPOCs in 16 clock cycles, at the same time, when we take the first one, when we take this guy, when we take this, yeah, we XOR it with this, with the neighbor one as well. Yeah, and save the output here. Yeah, but everything is also, of course, shifted byte-wise, no? And it's rotated byte-wise, but not over the column, over the entire 16-byte shift register. And then but it happens only in 12 clock cycles. No? In 12 clock cycles, then you update, you calculate completely the next subkey, but then of course, you use them as well, you know, in the 16 clock cycles. In the first 12 ones, you apply this XOR. It means that you need also a couple of multiplexers or select signal, or again, something that, okay, which values should be stored here? Is it the output of this XOR or not? Because you have also the SPOCs output, which should be also XOR'd here and stored here. Then you have a couple of multiplexes. But the idea is to reduce that amount as much as possible, means just one 8-bit SPOCs, of course, a couple of multiplexes. Just 8-bit XOR and a couple of multiplexes. Good. This is the idea, but then one more thing, which is also interesting that you should consider. When researchers were trying to benchmark their implementation, they realized that, okay, if I have a byte serial implementation, I can also load them serially. I mean, not the plain text and ciphertext are loaded in 128-bit at once, is also given serially byte by byte. But in which order? In this order. First the 0, and then 1 and 2 and 3. Means that I need also a multiplexer here to say plain text, but 8-bit. The same for the key. Then you need also a multiplexer here and select, okay, I need to give the main key 8-bit by 8-bit. That's not bad, this is okay, but some other module should also control this. Some other module, if it's used somewhere, I mean, somewhere else you have 128-bit of the key, 128-bit of the plaintext, it should be loaded serially. You need a wrapper for that. And then a wrapper with, again, another register to load it, or a large multiplexer. It adds a lot of area. You can actually do it here. The plaintext and the key actually are given. And then what you do, you apply the first key addition and also the SPOCs at the same time during the loading. This is also possible, yes. Then you reduce the number of clock cycles. Then somebody said, hey, what happens in the shift rows actually? In shift rows, you are shifting in this direction. Of course, one of them once, the next row two times, and the other one 3 times. And said, okay, the direction is actually like this, and the same for the mixed column. Then probably it's easier or more efficient, less area, if you change the order of the plaintext which is given. Then if 0 and then 4 and 8 and 12 and then 1, 5, 9 and 13 are given, then you probably can make a more optimum implementation. The same for the key. This is also possible. And then what happens then during the SPOCs operation, you don't do from 0, 1, 2, 3, you don't do shift it like this, you shift it in this direction from left to right. And of course this comes out, means that zero, 1, 2, 3, 4, 5, 6, 7. Then this you shift it like this. It goes to the SPOCs. You have the add round key here. And this is loaded like this. And then everything is shifted like this. And 3, of course, is coming and is stored here in 14. And it actually was true. I mean, it saved a lot, some area. But then for the key schedule, you need to again shift in the other direction, to perform the shift for the key schedule to shift exactly similar to what I have explained here. During the key schedule, you need to rotate over. You need to rotate over the columns to be able to apply these SPOCs over this column only, and then shifting them here like this. Good. Now we can have a look at the implementation that I have provided for you. I changed the implementation in a way that the plaintext and ciphertext are loaded 128-bit. I mean, everything is in parallel, which I think it's necessary and usual instead of loading everything serially. And then, of course, I did not try to make everything as or the most optimum version, because you should also keep in mind that with respect to the area, we talk about the registers and clock gating and so on. Something else is also important that you may see in literature and the papers, that what we said that you have to put a lot of multiplexers into the design. And then some of these multiplexers are happening actually at the input of the register. It means that you have, for example, D0 and D1, and with one select signal, you select this. Of course, the smallest way is without the enable signal because everything is controlled or done by the clock gating. And then what is the point is that when these two modules are combined together, there is usually a cell into the standard library cells, which is called a scan register. Scan register is something related to the design for testability. I don't know whether you have heard about this at all, design for testability. When you build a large design, then how to check, for example, the intermediate values of your circuit is working correctly without any error. Or when the circuit is faulty, you want to find out at which position, which intermediate signal is faulty. There is a protocol and there is a standard for that. Means that inside the circuit, some registers are built like this register, and they are actually shifted completely. They work as a shift register. And these shift registers, which are scan shift registers, for example, you have a big combinational circuit, or it's not the only combinational circuit, like a milli and more machine, any kind of a circuit, sequential circuit, some intermediate signals are taken, and then they are coming to this multiplexer and register, and then multiplexer and register, and again multiplexer and register, and so on. And the output of this is also connected to the next multiplexer, and so on. And then a few control signals, like the clock of a scan, and then, for example, data for the scan, and then, input, and then output, and then select of the scan. What it does, it can, in one clock cycle, store these registers, which are extra added to the circuit. They can store the intermediate values of the circuit into the register fully in one clock, in one shot. And then afterwards, through one signal, here, output of the scan, you can read this serially. It means that you stop and you halt the circuit, the main circuit, and you read the entire intermediate values of the circuit serially, and then you can debug. Unless, if you don't have this option, then you have to have microprobes on your circuit. If it's super tiny and small with a very super or highly optimized technology, like for example, 7 nanometer technology, you don't have any chance to put microprobe on the intermediate signals to measure it, to probe it. And then this is just done for the testing the circuit. And of course, it adds area, and it's not always done in any design. And then, of course, for security reasons, this should not be available in the security applications. Otherwise, you can have intermediate values of, for example, the cipher, and then you can easily break the cipher. Or if it exists, it should be completely killed during by some fuses to disable these ports. But then this register, what you see, this is a multiplexer combined with a register, which is called a scan register, and it's usually super optimal. It means that the designers and, let's say, the engineers, semiconductor engineers, tried a lot to build this super optimum and super small. Then if you see that somewhere in your circuit you have a multiplexer followed by a register, you can replace this by a scan register and then save some area. These tricks also have been done pretty often by many different researchers to say, hey, I have a smaller implementation, or this is my record. I have the smallest ever AES implementation, and so on. Good. But I have not done any of this in these designs. What I want to say, this is a very normal byte-serial implementation, but there are many different ways to make it even smaller. Yeah, and this is roughly the same fashion as you have seen. I mean, doing the add round key, doing the sparks, doing the shift rows, doing the mix column, doing the key schedule for the sparks, and so on. Yeah, I mean, probably it doesn't make sense to go to the entire details of this design, but this is the general form, that there is only one instance of the sparks, there is one instance of the mix column, and so on. Yeah. I mean, if you are interested, you can have a deeper look at the design, debug it, simulate it, or run it on the FPGA by yourself to see how this works. Okay. Did you understand? I mean, everything's clear? Good. Now, what happened afterwards? There are a couple of other designs, even smaller than the byte-serial implementation. Some of them dedicated to FPGAs, some of them using the FPGA-specific components. I mean, you remember the block RAM? Yeah. I mean, of course, the block RAM are good components in the FPGA, but I mean, all of this, what you see here, they are not using the block RAM. No? Good. The first design that we want to look together is using FPGA dedicated resources. There are different types of the slices into the FPGA. If you remember, I mean, one of the sessions we talk about the FPGA, I explained the slice M, slice L, and the slice X. And actually, this is the configurable logic block or CLB design of the 7 series FPGA, Y7 series, because the FPGA that we have, the CMOD A7, is one of those FPGAs. Slice L is the simplest slice, means that the lookup tables have the normal functionality that you have seen. You can implement 6-to-1 or 5-to-2 lookup tables with them. But there are more complicated slices, like the slice M. Here, you can have the same functionality as the 5-to-2 and 6-to-1 lookup table, but you can have also some ways to write something into this lookup table. Yeah, we can see write 1 to write 6, and also some data that you can provide, and write enable, for example, and then you can use them as some kind of a memory to store the result or values. There is another one, slice X. There is a big difference here between the older technologies or older families. The Spartan 6 had another slice, which is called the slice X, which was also even more complicated when it was on Spartan 6. And this paper that I was talking about, this one, which was published 2016, this uses actually a Spartan 6 dedicated modules, and you can use actually distributed memories, in a slice M, means that you can have exactly similar to block RAM, you can have some memory bits inside the lookup tables, because we discussed about this before, how the lookup tables are built. There is a multiplexer tree and some register beforehand that stores the value of the lookup table inside, and then based on the input, which are the select of the multiplexer, it decides which output should be given as the output of the LUT. And this register you can actually save on it, and then Vivado also has some features like the IP distributed RAM, and then it uses particular LUTs or elements inside the slice M to implement those. The name of the paper is SCA, or Side Channel Attack Protected. I mean, completely ignore this protection and side channel attacks now. This is something which is not relevant to this lecture. This is relevant actually to other lectures that I offer in winter semester about physical attacks and countermeasures. But we can have a look at the implementation and also the paper. The AES works like this. You see here that the key and the data state are stored in distributed memory is RAM32M. They are called, they are type of a slice M, yeah, which are also available in your FPGA, in the 7 series FPGA. And then this big one that we will talk about is just a SPOX. Yeah? Of course, you can write a lookup table as a SPOX, but what you can do is we know that for every single output bit of the SPOX, we need an 8-to-1 lookup table, 8-bit input, 1-bit output. But we have at most 6-to-1 lookup table. Yeah? But 6-to-1 lookup tables in a slice L of the FPGA, you have some multiplexers here, which are in the slice L that you can use, means that you can use the entire slice as a lookup table for 8-bit to 1-bit. You see there are some multiplexers here and some multiplexers here. Then some of them are configurable. You can select that how the input should be actually selected and how to pass through. Yeah, and for example, those that they are dark, I mean, you said they are gray, you cannot configure. I mean, you can configure, but they are not, you cannot change them during the runtime. They come just from the configuration. The other ones, which are actually white here, you can, during the runtime, have the select signal for them. Most of them is working like this. Then the entire design of this box can be built by just 8 slices of a slice L, and you have key and the slice M for the, I mean, there is only one slice. Now, the interesting thing is there is only one slice for the key and one slice for the state, and then you need a large multiplexer, which one you give here to this, you select from this, and then there is another multiplexer here that how the output is actually updated here, and a mix column. First of all, let me show the implementation. For example, you can have a look at the implementation of the SPOX. Yeah, the SPOX is actually just like this. You have 4 instances of the lookup tables. This is exactly the 4 lookup tables in one slice. Yeah, and then of course this is the lookup table. This is the single bit output of the SPOX, and then some multiplexers, and these are dedicated modules. I mean, about this we already talked about before about the macros that you can instantiate inside the FPGA dedicated designs. For example, you say mux F7 and mux F8. You have to go through the, again, library guide for the HDL design and find out which multiplexers are available where. And entire of this can be implemented in one slice. You should keep in your mind that, again, FPGA dedicated designs, if you want to hard macro everything and you want to put them in one slice, then not here, but in the constraint file, you should actually tell that these are, for example, this here, LT0, LT1, 2, 3, and so on. They are in one single slice, to help the synthesizer to understand that you want to put them in single slice. For example, in Verilog and some other, for example, older version of Xilinx tools, you could actually give them their slice position exactly here inside the VHDL or Verilog, but nowadays everything is inside the constraint file. You need 8 of them with different lookup table to implement the SPOX output. Yeah, if you look at here, the SPOX is actually like this, just instantiating this guy with the same input 8 times and get the output. And of course, as I said, these are completely different lookup tables. 8 different types of this. Now we look at the benchmark a bit, that how slow it is. The AES core you see there is a data available and data ready and reset and the key. Yeah, you have the key and data in. Each of them again 8-bit byte-wise, I mean the serial fashion, and data output is also 8-bit, means that just every byte. And then it's also given here that during the initialization, the plaintext and the key should be actually given not at the same time. Yeah, you cannot actually have them at the same time. It means that each of them just loaded differently because they are saved in a 256-bit distributed memory. Then you cannot actually at the same time save plaintext here and the key here. Yeah? Then you have to one clock cycle save the key and another clock cycle save the plaintext. And for that reason, loading or initializing takes 65 clock cycles. Yeah. Then you have the key schedule. Of course, many things are merged together, but in a byte sequential fashion, it needs 50 clock cycles, which is merged with the round function and requires 4 box computation and 17 Galois field additions. I mean, this is the XORs. Then the round function is implemented like this. I mean, everything is explained in detail here that the shift rows implemented. This operation can be realized using the address translation for either the loading or storing addresses. You don't need to spend any time for the shift rows, because the values are stored in the registers and the register have addresses. You read from one address, you write to another address in another distributed memory. Then you don't need to perform the shift rows on the state by itself because it's just distributed memory. And then the sub-bytes, I mean, we discussed about this lookup table. Then in total you need just 8 slices, and then of course it doesn't have any clock. I mean, it's just fully combinatorial. And one also thing which could save some area was the mix column. You learned already about the multiplication by 1 and 2 and 3. What it does, because it's just reading and writing from the memory, it says, okay, you have a temporary register, you read one value, and save it into register. This is multiplication by 1. And then you read another value from the memory, multiply it by 1. I mean, of course, it means nothing, and then XOR it with the previous value. And again, another one you take, multiply it by 2, and then XOR it with the result. Until in 4 clock cycles, you have the single byte of the output of the mix column. Means that again, 16 bytes multiplied by 4, then those many clock cycles you actually need, at least for the mix column, because this register has 8-bit wide, is 8-bit wide, and then how many clock cycles you need? As I said, at least 4 by 16 means 64, but may have some extra overhead by reading and writing into the memory, but I don't think it's the case. Then the key addition and the last round, in total it takes pretty long to read and write and perform the operation, but this should be one of the smallest implementation of the AES inside the FPGA. But keep in your mind, this is an FPGA dedicated design using the distributed memory. I mean, you cannot synthesize this for ASIC. For example, I can show you the AES core, and here is RAM 32M. This is the key state, and again the round state, and these are the hard macros of the FPGA, and you cannot have them in ASIC. These are fully dedicated to the FPGA. The next design that we want to show, or we want to see, is another topic which is called bit sliding. I guess you learned something in software called bit slicing. What is bit slicing? you have software implementation, right? For example, I mean, it's not dedicated to crypto, but this has some benefits in the crypto implementations as well. Suppose that you have the SPOX operation. Do you remember? I mean, you don't have any lookup table, but you have the SPOX operation of the AES, and then you write all the operations using just AND and OR and XOR and so on. Yeah, but of course, I mean, can write the SPOX you have seen, XOR, NOR, XNOR, AND and NAND and so on. But you can have also write this as a sequence of operations for software. Just similar instructions that AND of these two and read from the memory, or don't read from, just write everything from the register, but you can do it as like this. But then every single operand is a single bit in this representation. Yeah? But what you can do, you can have the CPUs which have 32-bit instruction or 32-bit operands, and then you can load into the register or this memory the input of the SPOX of 32 different operands. 32 different, but you need to just change, or let's say you have in the memory, you have 32 different values, and each one is 8-bit, from 0 to 31. But then you have to write it differently. You have to write it like this. Means that this should be in a register R0 from 0 to 31. And if this is, for example, here x0 and here x0, 0, and here is x07, and here is the x value 31, 0, and here this bit is x31, 7, then you have to change it in a way that you have here x this is actually R7, this guy. Let's call it R7. And then you have here X07 till X31, 7, 7th bit. And then you continue like this by R0, which is the LSB of everything, X00 till X31, 0. And then what you do, you run exact the same operation, instructions for software, but you actually apply this on 32 different operands. It takes the same amount of time, but you gain a lot. This is called bit slicing. Have you ever heard of it? Okay. And this, not only for the AES, but it's actually bit slicing is a technique which is useful for just software implementations, because the operands are larger. I mean, many years ago, the CPUs were just 8-bit, and then we have now in the CPUs, in the Intel CPUs that you are using in your laptop, they are 64-bit operands and operations, and then you can apply the same operations, the logical operations, on every 64-bit different values completely individually, but with the same instruction. For example, this has a very high benefit in simulations. If you want to run a simulation, logical simulation on some operands, but then you can do the bit slicing, and then you increase the speed roughly by 64 times. If your CPU supports 64-bit. Now, the same concept is not used, but bit sliding is something different. It slide 1 bit means that shift register what you have learned, when you have seen, means that what we said, you have to shift every byte per clock cycle for the AES, because the SPOX is large, but actually you can shift 1 bit. Now, who said you have to shift 8 bits? You can shift 1 bit. Once you reach the SPOX, then shift 8 bits. The paper is something that my group did a couple of years ago. Bit sliding, this is a generic technique, but let's see what happened for the AES. The figures are not super nice, but you can understand the things. This is the state of the AES. Byte 0, 1, 2, 3. I mean, they are also named differently, but you can see here the order of the shift is exactly what I explained. Instead of shifting it column-wise, we shift them row-wise. And then every clock cycle, you just shift 1 bit. Now, the mix column will be smaller because you have some XORs, which are single bit instead of 8-bit. And of course, some other NAND and NOR gates to control, because you have to then provide polynomial, the polynomial for the AES, also in a serial fashion, because you want to add or XOR this, if you remember, 1B hexadecimal. And then you have, based on the last bit, or the MSB, you have to select whether you add this polynomial or not. Then you need some extra registers for that. But then the plain text is also provided serially, bitwise. But then the SBox is a problem. SBox is there. You just load 8-bit and then update the 8-bit at the same time. That means that everything is serially sliding the bits, but then just the SBox is 8-bit because you cannot, at the moment, up to now, you cannot divide it into a smaller thing. Then the key schedule. The key schedule is like this. I mean, the same stance of the SBox is used, then you need another register here to save. I mean, I'm not going to explain all the details of this. This is super complicated to explain. If you are interested, you can read the paper. And also, I have provided the implementations for you also in the Moodle. I mean, not only the paper, also the implementations that we had. And we also cover not only encryption, I mean, the decryption, encryption and decryption together is also supported. Then you need to be able to, you may think of, you are shifting in both directions, but actually it's not the case. You just shift always from left to right and also in a row fashion. One important thing which we did not discuss together is that how do you implement the mixed column inverse, which might be, harder and larger than mixed column by itself. One property of the AES, which might be not known to you, is that if you implement a mixed column and again mixed column and again mixed column and again mixed column 4 times, you get 1. 1 means that if you apply mixed column or mixed column or mixed column O of X, you get X. Now, means that if you apply mixed column 3 times, you get mixed column inverse. Then, as I said, it doesn't matter how much it takes. Then the mixed column by itself is super slow, but doesn't matter, let's apply it 3 times. Then you have the mixed column inverse. And the same actually holds for the shift rows. If you apply shift rows 3 times, it's exactly similar to inverse of the shift times. Inverse of the shift rows. Then again, it takes longer, but you save some multiplexes. The control logic might be a bit more complicated. Then you can have both encryption and decryption and a design which takes longer compared to any other thing. Now, a bit of benchmark if you want to see. Here, what you see here, there are many different types of the bit sliding. Means that you can select, you can think of, 1 bit shifting or 2 bits shifting per clock cycle, or 3, we have 4 and 8, or 4 bit or 8 bit. 8 bit is the Byte-serial, and then the 1 bit shifting is the extreme case. But you can see that if you have just the encryption function, you need 1776 clock cycles just for the encryption. And if you have both of them, encryption and decryption, the encryption stays the same, but decryption needs 2512. Yeah, I mean, as I said, you are killing the latency. Yeah, but do you remember the gate equivalence that I explained before, how to compare the designs? Here, different columns are different standard libraries. NAND gate here 45, UMC, they are the commercial libraries, UMC 180, UMC 130, UMC 90, and NAND gate is an educational library. And then based on the gate equivalence, you can see also the size of the NAND gate. I want to just show you as a reference the size of the NAND gates, and these are already the gate equivalents. What is important is that you have one design, and then compiled or synthesized with different libraries, you see how big is the difference between their gate equivalents. I mean, if you remember, I explained before that gate equivalence it's supposed to be a fair way to compare different designs, but it's not the best way. I mean, might be the best way to divide this, dividing the area by the area of the NAND gate, instead of doing this, dividing this by the a subset of standard area of the subset of standard gates like NAND, AND, OR, NOR, XOR, XNOR, and so on, and avoid using super gates which are dedicated and particular gates of every library. For example, one AND OR cell might be available here, which is not available here, and so on. And you compile or synthesize with UMC 90, you have some benefits if you don't have UMC 180. Yeah, anyway, but in one single library you can compare, you can say, hey, you see, from moving from 1 bit to 2 bit, you have just 100 gate equivalents more, but even less, 50 or 70, 60 more gate equivalents, but you have much gain in the latency. Yeah? Good. And as I said, the designs are also available here if you want to have, encryption and decryption together, and some test bench. And again, keep in your mind that the test bench is also loading everything serially. Yeah, this because they are not, it's not built for just loading everything in parallel. And then if you want to implement them inside the FPGA platform that we have, you need to build a wrapper to load the data serially into this, and this already adds some area. For that reason, I don't believe that it should be like this. Otherwise, the other module which works with them should also feed the AES in a serial fashion. And everything is highly optimized. If you look at here, everything is tried to be optimized, but this is not an FPGA dedicated design. Yeah, keep in your mind that this speed sliding designs are general. They can be implemented in FPGA or ASIC. Yeah. This was just a register that we have seen, and everything is just a single bit. Yeah, these guys are just single bit values, and this is the mixed column which I have just explained and show you in the figure in the paper. And so on. If you want to have a look, you want to check by yourself, of course, feel free to do that. Good. The last design is something which is still speed sliding, but is using a particular property of the AES box, which is called rotational symmetry. It's a bit much into Boolean algebra. And this is the paper, and the design is actually dedicated to FPGA. Means that we try to optimize as much as we could just based on the FPGAs. First, I explain you the rotational symmetry. You have learned this already. You have learned that you have the box of the AES is Y. Let's call it. And let me write the bits of the S box input and S box output. Means that S of x7, x6 till x1 and x0. I call this y7, y6 till y1 and y0. They are just the bits of y and bits of x. You know that, how was the AES box? No? A box of x AES was x inverse over, and the result was going to an affine transformation. Yeah? And what is x inverse? In Galois field 2 to the 8. But how can you represent x inverse? You can say x is multiplied by x inverse. The result is 1. Yeah. But for me, the question is, what is this guy? Yeah. I mean, generally, xm multiplied to xn equals what? X to the m plus n. Yeah. But in Galois field 2 to the 8, what is the maximum value of this? I mean, this is rotating. This is a kind of a ring. Yeah. This actually equals x to the m plus n modulo 255. Yeah. Then if you write it like this, you can write x minus 1 equals x to the 254. Yeah, because if you add them together, add them to x plus x, yeah, should be modulo 255 and should be 1. Should be 0. Huh? Should be 0, then x to the 0 equals 1. Then these operations, yeah, they are called power functions. Yeah, power functions. And why I have explained this, because to tell you that x inverse is also a power function. Yeah. And in normal domain, if you have a normal domain, again, Boolean algebra, if you haven't, I don't know whether you have learned normal field, but in normal field, the power functions are have rotational symmetry. Rotational symmetry means that if I have a power function, and this is in the normal field, then f of, again, x7, x6 till x1 and x0, if I call this again y7, y6 to y1 and y0, I can find a function, yeah, which actually provides this, which is the first coordinate function of the f. Yeah? And the interesting thing is that the other outputs I can build with the same function over rotated inputs. Means that I rotate the input, I get the next input, the next output of the function. Means that you can have the same function, which is one coordinate function, and then rotate the input and get the other output bits. And since you have learned that the AES box is inversion plus an affine, then the inversion is also a power function. And if you bring this power function into the normal field, then you have this rotational symmetry. Then instead of implementing 8 different coordinate functions, for each of the SPOC's outputs, you can have only one coordinate function and then use it 8 times over the rotated input and then implement the AES SPOCs in 8 clock cycles. And this is exactly what happens here. Yeah, and look at just at the left side. What is this P to N? You need to bring it to the normal field, means that it's the polynomial field to the normal field, and this is just an isomorphism, means that it's just a couple of XORs. And then it's 8-bit to 8-bit just the XOR. Then you have here the 8-bit value, which is in the shift register. What you do, you apply this S star. The S star is exactly the coordinate function of the x to the 254, the inversion, but in that normal field. And then what you do, you actually shift this or rotate this, you see, 1 time from left to right. And then here you can also shift the value here, the output, and then in 8 clock cycle you implement the inversion in the normal field, and then again another isomorphism from normal to polynomial form, and then you get the y. No? Of course, see, there is another one here. I mean, if the input should be loaded in parallel 8-bit or the bit should be loaded in serial, means that if it's loaded in serial, it loaded here 1 clock cycle, the P to N polynomial to normal is applied, and then afterwards 8 clock cycles, this S guy, and then after 8 clock cycle you have another one N to P normal to polynomial, and then afterwards you have the exact a SPOC's output if you combine normal to polynomial form isomorphism if you combine it with the affine transformation of the AES SPOCs. Now this is what also was performed by Candride SPOCs. Yeah? The isomorphism are also combined with the affine to make it, of course, more optimized and compact. And what we did, I mean, in this design, is combining the last 2 designs that I have explained you, bit sliding and also using the FPGA dedicated resources. Instead of using the distributed memory, what you can use the shift registers by the lookup tables. You remember again that some slices have shift registers. I mean, the lookup table here can be used as a 32-bit shift register, SRL32, which is also dedicated to particular slices of the FPGA. And then instead of having registers, then you can use SRL. And this gives you already 32-bit register for you, but shift register means that you cannot easily change or read the intermediate value. I mean, you can read, if you change the address, but you cannot change something in the middle. Writing is just shifting and then updating one single bit. Then this is actually the entire story about SPOCs. And then the rest, if I find something here, the rest how the design works, they are, you see here the shift registers that they load the data, again plain text, serially, but bit by bit. And then the SPOCs, I mean, the output is also here given to a SPOCs in a also serial way or serial fashion. And the mixed column is similar to what I have shown you for the bit sliding design. It means that the mixed column also updates 1 bit per clock cycle, because you cannot change something in the middle. Everything is just bit serial, and this is the smallest, I mean, up to my knowledge, this is the smallest implementation which could be done for the AES, but of course, as I said, dedicated to particular FPGA families. There is a benchmark somewhere. Yeah, I think this is like this. The number of loots and number of flip-flops, number of slices. What you should consider, I mean, some of the designs are in FPGA, they are compared based on their number of utilization, I mean, amount of utilization, how many loots are used, how many flip-flops are used. But sometimes it's too complicated for the FPGA tool to fit them into the FPGA. Yeah, I mean, you can, for example, count, yeah, how many loots I have, 84, but divided by 4, how many slices it is? No, it doesn't work like this, because then the routing capacity and possibilities in the FPGA are restricted. You cannot have the full utilization of the resources. Usually, the best design usually which fits on an FPGA is 80% utilization. Yeah, you can almost, I mean, never use all the resources of one FPGA. Yeah, because the routing doesn't allow you. No? And here you can see that the smallest design that we had, I mean, based on the number of loots, is 64. Yeah, 63. Sorry, 63 loots. Number of flip-flops. Yeah, some other designs use less, some other designs use more. And then the best design based on our knowledge is this one, which using only 17 slices inside the entire FPGA without using the block RAM and so on. But of course, you see, you kill the latency. Yeah, I mean, 5,500 clock cycles just for one AES encryption. No? Okay, and of course the design of this is also provided for you if you want. I mean, everything, but keep in your mind this is highly dedicated to FPGA and highly optimized for the FPGA. For example, even if you look at the controller, everything is based on lookup tables. I mean, it's absolutely impossible to understand what it does. Yeah, because we try to optimize everything manually. I mean, we wrote everything and then we say, okay, this function is a 5-bit to 1-bit function. It is another 5-bit to 2-bit function, and optimize everything manually, and then write another program to give the functionality that we want, to generate the lookup table, and then write this lookup table here that you see. Yeah, I mean, you cannot really find out what it does. Yeah, this is highly optimized just based on the components of the FPGA, because the idea is, okay, to use as much as possible means that, I mean, the resource, not as many as possible, not many resources, but for example, if you have a loot of 5 to 2 and then you use just 2 inputs of the loots, you are losing some of resources. Yeah, I mean, to fully use the resources that you have. I mean, if you look at here, there might be some cases that, you see some inputs are 0. Yeah, this is pity. Yeah? You are not using that facility. I mean, but I mean, this we could not probably make it even better than this. Yeah, somewhere we had to put 1 or 0 or something to. I mean, some functions are. I mean, you have, for example, 8-bit to 1-bit function. I mean, then you can calculate how large are the loots that you want to use and so on. Good. I mean, these implementations are also available for you in the Moodle if you want to have a look. I think there are not much else to say about this. The rest of the paper is something which is not relevant again to this lecture. It's again about protection against side channel attacks. That we will review actually this topic at the last session of this lecture. I mean, the last session I will explain you some other things with respect to the security of the implementations. And then we will see, or you may check whether you have any interest to join the other lecture of mine, which is offered on winter semesters about physical attacks and countermeasures.